Give a standard logic puzzle to the top 3 AI models available right now, and they all pass. We fed the classic Monty Hall problem to Kimi, Claude, and GPT-4o to see how they would handle it. Within seconds, every model produced the same result. You should switch doors. Grading an AI purely on the final output hides the logic used to reach it, and those differences dictate whether a model stays reliable when the parameters change. While the input and output look identical, each model takes an unseen path through its own internal processing space. This creates a challenge for users. When every AI passes the standard tests, it becomes difficult to know which tool to trust when unexpected variables enter a workflow. Reliability depends on identifying which specific data points a model prioritizes when you hit enter. Mapping these unique cognitive architectures helps clarify why a model succeeds in one task and fails in another. To see these differences in practice, we can map the reasoning Kimi, Claude, and GPT-4o used for the Monty Hall puzzle. Kimi scans for constraints first. It identifies that the host's action, revealing a goat, is a fixed rule. That rule leads to the consequence, which generates the answer. This is a systematic approach. It prioritizes the logical structure of the game over any intuitive gut feeling. Claude follows a similar logic. As the middle section shows, it anchors to mathematical probability, noting that the initial 1/3 chance remains invariant even as new information appears. The trade-off for this accuracy is a highly technical explanation. Kimi and Claude provide precise answers that can be difficult for a general user to digest quickly. GPT-4o takes a different path. In the final column, we see it bypasses the strict math to reframe the problem, explaining that switching is like choosing 2 doors instead of 1. This makes the logic feel intuitive and easy to follow. However, this reliance on conceptual shortcuts abstracts the raw data away from the actual logic of the system. These diverse pathways all work in standard scenarios, but the difference in their foundations becomes clear the moment the environment shifts. We can stress test these models by introducing a single change. The host forgets what is behind the doors and opens one at random. This simulates real-world complexities where the standard rules of a system no longer apply. Look at the flowchart. When the host forgets variable intercepts their paths, Kimi and Claude flag it immediately. Because they anchored to the math, they adjust their probabilities to reach a new, correct conclusion. This rigid logic ensures accuracy in edge cases, though it often requires users to provide hyper-specific prompts. GPT-4o, however, attempts to apply its previous intuitive shortcut to a system where those rules have changed. The logic path dead ends. The model generates a confident answer that is mathematically incorrect. Using abstraction to simplify a problem limits a model's ability to adapt when the core rules are modified. This explains why models can fail during complex professional workflows. They aren't just breaking. They are applying shortcuts to situations that require strict logic. These results suggest a specific way to choose which model to use for your own work. This decision matrix aligns each model's cognitive architecture with the requirements of specific tasks. For programmers, data analysts, and researchers, Kimi and Claude are the strongest options. They excel in the logic and math workflows shown here. These roles require strict adherence to rules, especially when handling the edge cases common in technical fields. Conversely, they are often less effective for creative workflows, where their rigidity can make brainstorming feel stalled. GPT-4o is better suited for marketers, educators, and strategists. These roles require an AI that can synthesize information and reframe concepts for an audience. As the X marks show, its performance drops when changing the core rules of a logical system without human oversight. Ultimately, mastering AI means matching the tool's cognitive architecture to the specific problems sitting on your desk right now.